Have you ever wondered how AI captures meaning and similarity and how you can build it step by step in C#? Hey, it's Michał from DefaultAzureCredential, and today I'm showing you how to finally make sense of embeddings, and it's way easier than you think. By the end, you will know exactly how to represent text as meaningful vectors. You will also understand how similarity metrics behave, and you will see which embedding models are available in Microsoft Foundry and how choosing different models influences your results, all demonstrated with real C# examples. So, let's dive in. Hey, I believe that working through examples is the most efficient approach, which is why I've prepared 4 of them. Working through these examples in this order should make it easier to understand the concept of embeddings. So let's not waste any time and let's jump straight to our examples. So let's imagine that we have such an objective. So there are 4 terms: Mars, Apollo 11, Neil Armstrong, and Curiosity rover. And our objective is to measure similarity between them. So all of these terms sound similar, but not in the same way. Mars is a planet, Apollo 11 is a mission, Neil Armstrong is an astronaut, and Curiosity rover is a robotic explorer deployed on Mars. So now, without any math, just purely on our intuition, we may conclude that Mars and Curiosity rover are very similar, as well as Apollo 11 and Neil Armstrong. But how can we measure that similarity in our C# code? So it won't work if we just compare these terms. So one way to address this challenge is to define a set of attributes which define each of these terms. So let's go to the attributes example. And as you can see, we have a dictionary with all of our terms, and on the right side you can see attributes, and each of these attributes represents or defines the term which is on the left side. And as you can also see, we use a finite number of attributes, so we have just 3 attributes, and it's just sufficient for our tiny example. So our job is to measure similarity between each of the term versus the remaining terms. So let's see how the get the most similar items method looks like. So the only input parameter is the search keyword. So what we do, we take attributes assigned to that search keyword and we compare them with attributes assigned to all of the remaining keywords. So we use the intersect method, and then we measure the percentage, knowing the maximum number of attributes which may overlap, and then we just assign it to similarity property. What we do at the end, we just order the results in descending order. So as simple as that. Let's see how it works. So if we compare these results with our earlier intuition, you'll see that they line up almost perfectly, with one interesting exception, which is Curiosity rover. So as you can see, Mars, Apollo 11, and Neil Armstrong are equally similar to Curiosity rover. And it's a great example of why simple attribute search might not be enough, but it's a good starting point. So let's improve it now. In order to improve our previous example, let's make one small adjustment, which is an adjustment that you'll see soon is essential for understanding embeddings. So the key change in the second example is to convert our array of strings into a numerical representation, a primitive vector. So let's look at the dictionary. So for the Mars term, we have true, false, and false defined, or 1, 0, and 0. And this is because this simple matrix at the first column represents the planet attribute, whereas the second column represents the mission attribute, and the third one, the astronaut attribute. So if we look at this vector with just 3 dimensions and we compare it with what we have defined in the previous example, you'll see that the meaning has been preserved, but the representation of it has changed. And this change is significant because now we can implement our first vector search. So if we go to the get the most similar items method, you will see that what we do now, we compare the search vector with a corresponding other vector. And we check if at the given position, value is true for both. If the answer is yes, then we increment the counter and everything else remain the same. So let's invoke it now. So as you can see, results remained the same. But even if results that remain the same, the change is really important because now we are not using array of strings anymore. We use vectors, and we can therefore perform a vector similarity search. And by the way, if you hear a term, a vector embedding, or an embedding, they usually mean the same thing. But you can think of it this way. Vector is just a list of numbers. It doesn't mean anything on its own. It's more like a mathematical term, whereas an embedding is a vector which carries a meaning. In our case, it carries a meaning about the planet, the astronaut, and the mission attribute. But if we look at the results, they are not as accurate as they could be, especially for the Curiosity rover. So let's improve it further. Let's finally enhance the quality of the results. So let's look at the binary vectors from the second example again. So if we look at them, the question arises, can we nuance these assignments of attributes somehow so that they can express how strongly given attribute applies to a given term? Currently, with these primitive binary vectors, all we could do is to decide whether a given attribute applies or doesn't apply at all. But as we all know, reality is more nuanced. So let's do something with it. Let's jump straight to the third example. So in the third example, instead of just assigning 0 or 1, we use double, as you can see. And the idea is following. We can assign any value from 0 to 1 and within that range, where 0 means no relation at all and 1 means the strongest possible relation. So let's see how it's defined for the Mars term. So at the first position, which represents the planet attribute, we can see the highest possible value, 1. It's because Mars is a planet. At the second position, we can see 0.2 because Mars is slightly related to missions. And at the third position, we can see 0 because it's not related to astronauts. You can claim it is somehow related, but let's keep our example very, very simple. So now, I hope you get the idea. So let's invoke the method, and then we'll check how we measure similarity. So as you can see, results are now way better. And I think they pretty accurately reflect the reality. If we look at the Curiosity rover, 0.80 for example, but then we have like Apollo 11 and Neil Armstrong 0.99, yeah, it makes a lot of sense, right? And even if we look at the differences between these positions, it all is very understandable and reasonable, in my opinion. So now let's focus on how we measure similarity having these primitive vectors available. So as you can see, first of all, what changed is not what we compare, because we compare the other vector with the search vector. It's about how we compare. And in order to explain that, I prepared a simple diagram. So if we look at that 3D diagram, it represents our vectors in three-dimensional space. So we have three axes within this 3D cube. So the first axis is the planet axis, then we have the astronaut axis, and finally the mission axis. And I applied all these values from the C# example to that 3D cube so that you can visualize it easily. And by the way, this is also the reason why I chosen like 3 dimensions. For us humans, it's just easier to visualize such things in 3D space. So let's look at these vectors. So the idea is following. To say whether two vectors are similar in 3D space, we can use various techniques, and I'll get to it in a second. But one of the most common techniques is called cosine similarity. So what cosine similarity does, it measures the angle between two vectors. And if the angle is relatively small, it means that two vectors point in the same direction, which means that similarity is very high. So now going back to our C# example, what we have here, we just have a simple math formula translated into C# code, which calculates the angle between two vectors in three-dimensional space, in a space of any dimensions, really. And you may now wonder, hey, do I need to implement such logic yourself? No, you don't have to. Usually, you will just choose within a given vector database provider which method you want to use to measure similarity between vectors. But I just wanted to show you that if you want it for whatever reason implement it yourself, it's still fairly simple. So we measure the similarity between two vectors by measuring the angle between them. And once we have that cosine similarity calculated, we again assign it to the similarity property so that then we can order the results in descending order. Cosine similarity is just one of the methods, and I think it will be very beneficial for you to learn even a little about the most common similarity methods. Let's discuss the most common similarity metrics right now. So let's go back to our 3D cube and let's finish the cosine similarity. So we've already discussed the basics of cosine similarity, but let's talk about what results can be returned by this method. So cosine similarity can return a value from a range from -1 to 1, where 1 means the strongest possible relationship. 0 means that two vectors are perpendicular, which means that there is no relation at all. -1 means the strongest negative relation. So this is what you should know about cosine similarity. The next common similarity metric is Euclidean distance. So if we look at the 3D cube, Euclidean distance is like drawing a straight line from the Curiosity rover, for example, vector to the Apollo 11 vector. And another method which is very similar to the Euclidean distance is called Manhattan distance. It's also about drawing a line, but it won't be a straight line. You need to move along the axes. And this is why it is called a Manhattan distance, because it's like walking in a city with a grid of streets. Yet another similarity metric is called dot product. And dot product is something which we've already used to measure cosine similarity. So dot product is all about multiplying one vector with the another. So as you can see, we multiply values at a given position and then just take a sum of it. The last similarity metric which I would like to discuss is Hamming distance. And Hamming distance is super useful, especially for binary vectors. So this is our second example. So we've used such logic to measure similarity, but in reality, Hamming distance uses XOR operation and pop count operation. And it's super fast because, these two operations are invoked at the CPU level. So it is the fastest way of comparing vectors. So I think this is a sufficient dose of knowledge in reference to available similarity metrics. So let's jump to the next example, to the final one. Up to this point, we've been playing in a tiny little sandbox, a three-dimensional space where each axis represented one attribute: the planet, mission, and astronaut. But it was a great mental model to build some intuition, but in reality, language is just too rich to squeeze everything in just 3 dimensions. So in reality, when you'll be working with vectors, you may expect hundreds or even thousands of dimensions. So one of the common dimensions is 1536. So you'll see it very often. And now you may wonder, like, hey, wait a second. If we worked with 3 dimensions, then how could I even interpret so many dimensions? Like, we had just 3: planet, mission, and astronaut. So the key point is you don't need to interpret them, okay? So an embedding model, which is responsible for vectorizing your data, whether it's text, as in our case, or an image, or a video, or an audio file, it knows the dimensions. You don't need to understand them at all. The only thing which matters to you is that as an output of an embedding model invocation, you get a vector which you then can compare to another vector. This is all you need to know. And you may wonder now, okay, but we applied various and we discussed various similarity metrics in reference to our 3D cube. So for example, measuring angle between two vectors in 3D cube. So we could visualize it somehow, right? But now let's try to visualize a space with so many dimensions. It's just impossible. I mean, it could lead to Stack Overflow exception in your brain, right? But what matters most is all of these similarity metrics are applicable to vectors with more dimensions. So it's more about computational expense, but everything remains the same, whether we compare a vector with just 3 dimensions or a vector with 1536 dimensions. So this is the key point to remember. Another term I would like to explain is an embedding space. So embedding space is where all vectors produced by a given embedding model live, which also means that you can compare vectors only within a single embedding space. So even if you have a vector with given number of dimensions, let's say 10, and another vector with 10 dimensions, you can compare them only when they come from the same embedding space, which means they were created by the same embedding model. This is really crucial to remember. So let's also talk about data modalities. So in our example, we are working with text. So we just convert a text into a vector and then compare it with other vectors, which were also created by converting text. It means that we work with a single data modality. There is possibility to compare vectors from multiple modalities. It's called multimodal vector search, and I'll cover that topic very soon on this channel. But comparing vectors within a single vector space, embedding space within the single data modality is a good starting point. And now I believe it's the right time to talk about Microsoft Foundry and embedding models that we can deploy there. See you there. Equipped with the knowledge from the previous examples, we are now ready to discuss the final example, where we'll be using a real embedding model deployed in Microsoft Foundry. And by the way, if you are surprised by hearing this name, Microsoft Foundry, then I understand you, because this service was initially named Azure AI Studio. Then it got renamed to Azure AI Foundry. And after the recent rebranding, the name is Microsoft Foundry. So just to make it clear, I'm recording this video in January 2026. So Microsoft Foundry, in a nutshell, is a unified Azure platform as a service offering which allows you to build AI-powered solutions so that as a developer, for example, you can focus on building things rather than creating and configuring some infrastructure. So it simplifies a lot of things. You can deploy various models. You can configure various integrations with Azure AI services, aka cognitive services. And you can apply various content safety metrics as well. And there are many other features which are available. But since the topic of today's video is embeddings, let's focus on this part. So if we go to the build section and then to models, you'll see that I have 3 models deployed already. And I'm going to leverage text embedding 3 small and ADA002 embedding models in the 4th example. GPT 4.1 mini cannot be used for generating embeddings. Model capable of generating embeddings is a specialized model, and it's not the same model type that you would use in your chat-like application. So if you want to deploy a new model, you just click on Deploy a base model, and then you should choose from the available models. And as you can see, the number might be a little overwhelming, so let's narrow these results down a little. So I encourage you to go to Inference Tasks and then choose Embeddings. So now we still have 100 models available, but I'm going to use the ones provided by OpenAI. So I'll go to Source and choose Azure OpenAI. So as you can see, just 3 models remained, and 2 of them are already deployed in my research. So I won't be deploying them again, but if you want to deploy such a model, it's as easy as clicking on it and just clicking deploy with default settings, unless you want to configure some custom settings like token limits per minute, etc. So these are the basics of the Microsoft Foundry portal, especially in reference to embedding models. But there is one more thing I would like to show you, which is how this resource looks like from the Azure portal perspective. So as you can see, in Azure portal, you can see some basic settings like access control for assigning role-based access control, keys, networking, encryption. But if you want to configure some specific settings, then you cannot do it from here. You have to go to that dedicated portal. And of course, you can configure everything using Azure CLI and ARM.json and Bicep. Okay, so I think it's all we need to know for now about Microsoft Foundry. So now let's jump to the C# code. Let's focus on the C# code now. So let's start with the dictionary. As you can see, there are no vectors, there are no embeddings, because we are going to generate them using embedding model deployed in Microsoft Foundry. So all we have are the terms that we've already used in the previous examples. So now let's focus on this logic here. So in order to connect to an embedding model deployed in Microsoft Foundry, you should pull 2 NuGet packages. You should pull Azure AI, OpenAI, and Azure Identity. So we just need 2 variables. The first variable is URI of our Microsoft Foundry resource, and the second one is the deployment name of our model. So if we look at these variables, this is something which you can easily find in the Azure portal or in that dedicated Microsoft Foundry portal. And deployment name is something which you can easily find in Microsoft Foundry as well. So if I go to the build section again, to models, these are my deployment names, okay? So if I search by that term, it will be found. And by the way, by default, deployment name equals given embedding model name, unless you decide to change it. So we just need these 2 environment variables. And now you may wonder, hey, why we are not using this API key, which is shown here. So we are not using it because it's not the right way of doing things in Azure if you pay attention to the best security standards. So the way it works in this example, it uses DefaultAzureCredential class. So this class comes from Azure Identity NuGet package. And what it does, it tries to pull a token from various token providers. So if we look at these token providers which are available, we'll find providers like environment credential, managed identity credential, which is very often used in production. But when I invoke this example on my local machine, I'll be using this Visual Studio credential. And it will be capable of authenticating my user because of 2 reasons. First of all, if we go back to Visual Studio and if we go to Tools, Options, Azure Service Authentication, Account Selection, you will see that I logged in with the account, which is also available within the Entra tenant in my Azure subscription. So this is one reason I logged in here. And the second reason because this is not sufficient. My user must have necessary permissions assigned. So if we go to Azure portal one more time, and if we go to access control, I can click on view my access, but let's go to role assignments. And as you will see, I have Azure AI user RBAC role assigned to my security principal. And it is assigned at the subscription level and as well at the resource group level. So role-based access control assignments are propagated down in Azure. So if I have it assigned at the subscription level, then that assignment is automatically propagated at the resource group level and at the individual resources level. So thanks to these two configurations, now I can just invoke that code and it will first fetch a token because I configured it correctly in Visual Studio. And second, it will check that I have necessary permissions to access Microsoft Foundry using Azure AI user role. So I'll be able to use it. Now that we've confirmed that our embedding model is capable of authenticating to Microsoft Foundry, let's finally invoke the last example. So let's put a breakpoint here to make sure our items dictionary gets filled in with embeddings coming from Microsoft Foundry. So let's run it. Okay, if we look at our items dictionary now, you can see that for each of these terms, there is an embedding pulled from our deep embedding model. So just let's look at some values. As you can see, the range is from -1 to 1. So that looks good. And now we can compare our terms. And by the way, we'll be measuring cosine similarity, but in a slightly different way. So instead of using that that custom C# logic that we are looking at in the previous examples, I'm using here TensorPrimitives cosine similarity method. So it calculates cosine similarity the same way in terms of mathematical formula, but it is just optimized for the best performance. In order to use TensorPrimitives cosine similarity, you should pull system.numerics.tensors NuGet package. Okay, let's continue. So as you can see, the embeddings were automatically generated and then similarity search was calculated using TensorPrimitives, and here are the results. So the results overlap with what we have seen in the previous examples, but there is a great step forward because we weren't assigning any attributes manually, they were generated automatically. And in addition, in the last example, I decided to create 4 sentences to just see if it can capture really that meaning or not. So for example, the planet next to Earth, but not Venus. So Mars is at the first position. That looks good. The first mission that carried humans to the moon, Apollo 11. The first person to step onto the lunar surface, Neil Armstrong. The NASA robot exploring Mars since 2012, Curiosity rover. So, as you can see, it is pretty accurate, but I haven't told you we used less powerful model in this particular invocation. So what I'm going to do now, I'm going to leverage the second embedding model I have deployed in Microsoft Foundry, which is text embedding ADA002, which is more powerful model. So let's change the deployment model And let's invoke the example for the last time. Okay, so embeddings were generated. So if we look at them, as you can see, the dimension remained the same. Dimension remained the same, but this model is capable of capturing more meaning. So dimension doesn't mean that, higher dimension translates into a more powerful embedding model automatically. No, you just need to know which models are more or less powerful, and you won't be using the most powerful models for some easy tasks because they are just more expensive than the more primitive ones. So you always need to adjust the model to your needs, and then you need to establish a correct evaluation pipeline of your AI solution so that you will be able to decide which model to use. It's a topic for a separate discussion, so we'll cover that in the future. Let's continue to see the final results. So as you can see, the order of items remained the same, but what has changed is the similarity metric. So these numbers are around like 80 or 90, and it all looks good. Let's check something randomly. The first mission that carried humans to the moon, Apollo 11. The NASA robot exploring Mars since 2012, Curiosity rover. So it did its job. So I think this is sufficient dose of knowledge for today. So thank you very much for listening and watching, and see you in the future. Thanks. Thanks for watching. The goal of this video was to lay the foundation for the more complex topics I'll be covering on this channel. I hope this video helped you better understand how embeddings capture meaning, how we measure similarity, and how to deploy an embedding model in Microsoft Foundry, and then how to authenticate your C# application using RBAC and best practice security. I'm really interested in how you plan to use embeddings in your own C# project, or if you've already implemented them. I'd love to hear what works for you. Feel free to share your plans or experience in the comments. And if you want more content on future-ready AI solutions deployed in Azure using C# and .NET, not Python, please hit the like button so I know such kind of content is valuable to you. Thanks again for your time and watching. See you in the next one.